All right, so today, in section 13.2, we're continue to study curves, and we're trying to learn how to find the length of the curve. And this is a kind of introduction to geometry, to curves and surfaces, geometry of curve and surfaces. So we are focused on curves right now. So given a curve, right, and then the moving object in the space, yeah, this is a moving object in the space, okay? So we know that, and how do we describe this origin, right? So this is our t. So this is the tangent vector, okay? So the tangent vector will be in that direction. That's the tangent vector. And it's defined to be the limit as h approaches 0, rt plus h minus over t divided by h. So from the definition, you can tell that this is a limit. The limit should be a vector tangent to the curve. And this is usually called in physics called the velocity vector. Okay. Yeah. Of this moving object. And the length, okay. So if it has 3 components, okay. So let's assume that x is xt, yt, and zt. Then the length is going to call the speed. So this will be the square root of the first term, and the second term, and the square root of the square of the first term plus the square of the second term plus the square of the third term. Okay, so given vector, and how do you measure? This is this tells you how fast of the moving object. This is the speed. And there's a difference between velocity and the speed. So let's take a look at some examples. Assuming that the position vector of the moving object at given time t is given by this formula, right? So you have 3 components here, right? When t changes, all those components changes. And we want to find out the velocity vector at t equal to 0, at t equal to 1. All right. All right, so all you need to do is find the derivative, and then you differentiate the first term. The second term is just 1 minus 3t squared, and then 1 over t. All right, so now when t equals 1, so when t equals 1, that's going to be e to the negative 1 here, and 1 minus 3 times 1 squared, 1 over 1. Okay, 1 over 1. All right, we simplified. Then you get the rest. -2 and the 1. Once you know the velocity vector, and this is also the tangent vector to the orbit, right? So you can also, then you can also find the equation for the tangent line if you want. Okay. So let's take a look at problem from the book. It's problem number 19. So you are given this function, position function, cosine t, and I think it's 3t. To sine 2t. Now, if you use a program software to like a mathematical or Maple, you can actually draw the graph for this. And we want to find out the unit tangent vector capital T at t equal to 0. Okay. Now we can just find the general formulas and you normalize it. So we have to solve this type of problem, I think it's the best to be write on the formula before you even started to find the derivative. So the formula is going to be the derivative, the tangent vector, you normalize it, so you have to divide by the unit, by the length of its curve. Then you can show that this is a unit vector, okay? Let's find out the derivative. So that will be negative sine t, 3, and the derivative sign becomes cosine, but then have a 2 there, so it's 4 cosine 2t. Right? We have to find the length because this is not a unit vector. Right? So you find the length for cosine 2t squared. Now it's harder to simplify. So in order to find the unit tangent vector at t equal to 0, I don't need to get the general formula. I just needed to evaluate when t equals to 0, right? This one, yeah, we find both of them, okay? So the vector becomes negative sine 0, 3 cosine 2 times 0. Cosine 2 times 0 is 0. So it's going to be 0, 3, and 4, right? So the length is going to be 0 squared plus 3 squared plus 4 squared, which is 5. Yeah, 3 squared plus 4 squared is 5. Okay, so the t at the 0, the unit tangent vector 0 is going to be, and you normalize it, divide by 5. Now this is this actually is going to be 1 over 5 times 0, 3, 4, okay? Or you can multiply this out, 0, 3 over 5, 4 over 5. Yeah, simply express as a simple, as a single, yeah, just one, it's a vector notation, yeah, use it. All right. So now let's go over the cross product. Okay, given two vectors in the space, you can talk about the dot product and cross product, right? The dot product is just a number. It is going to be that's A, that's a B, right? If this angle theta, cosine theta. The cross product is a new vector, okay? It is perpendicular to those two vectors, okay? So this has a following two property. One is perpendicular to A and B. Second, the direction should be determined by the right hand, right, from A to B, right? So the direction should be going like this, okay, from A to, right? It's determined by this, okay, from A to B, okay? Rotate from A to B. Okay, the third one is the length. You have to determine the length. The length is going to be sine times this. So based on yeah. Now the geometric meaning of this is going to be the area of the parallelogram spanned by A and B. Right? This is actually the area of the parallelogram spanned by the vector A and B. Okay? Just because the length of B times sine theta becomes the height of the parallelogram. The base times height gives you the area of the parallelogram. All right. Now, if you want to come to the detailed formula, then A dot B is going to be A1, B1, A2, B2, A3, B3. Okay? But the cross product is you have to use a vector. It's a vector, right? So you have to get three components. The three components is determined by this formal determinant. Okay, it's A1, A2, A3, B1, B2, B3, and you should expand it. Okay, so you get three components of the expanded along the first column, right? How do you find the determinant of 3 by 3 matrix, right? You, along the first column or any column, right, you can expand it. You get three terms. All right. So basically, this term is going to be the determinant A, I think A2, A3, B2, B3. After you delete the first column, first row, and this will be negative, change the sign, and the first row and the last, first column is the last column. And the last one will be the first column, second column. Okay, so those are the three components, right? Right, so take a look at the example. We have e to the 2t, e to the negative 2t, t times e to the 2t. Now, it's hard to draw the graph here. I just sketch the graph in some way. What I'm trying to find out is, I want to find the unit tangent vector. And I can also use this to get, okay, this is a unit tangent vector. But gamma prime t may be shorter than that, okay? But you also have another vector, you get gamma double prime t when you continue to differentiate. Right? Gamma prime t and the gamma double prime t is two vectors are not linearly independent, are linearly independent. So you can use that to create another vector perpendicular to the tangent vector. Okay. So Yeah, let's see. First of all, yeah, the unit tangent vector is determined by this formula, right? Right. If gamma prime t and gamma prime t are linearly independent, most of the times it's linearly independent. So there can then the cross product is not going to be zero. Okay, then gamma prime t cross gamma prime t is not going to be zero. Okay, so you can also normalize it. You can normalize it. So you get another vector. But I know this is vector, yeah, so I can define nt and normalize it. Now, what is the property of those two vectors? I think nt is perpendicular to t. So because this this product, right? This cross product is perpendicular to gamma prime, right? So this implies their ratio, right? This nt will be perpendicular to unit tangent vector. So you along the curve, you differentiate the function twice, you get two vectors. One is a tangent vector, another one is perpendicular, another vector perpendicular to tangent vector. Right? But the computation is the general formula is very complicated. Right? The general formula is complicated. We can try. Yeah, we can try. Right? So gamma prime t is going to be 2e to the 2t, negative 2e to the negative 2t, e to the 2t plus 2t e to the 2t. Okay, so that is a derivative. And you can continue to differentiate. So if you continue to differentiate, you will get 4e to the 2t. And this will be also 4e to the negative 2t. And here a little bit complicated. I needed to do calculation here. 2e to the 2t plus 2e to the 2t plus 4t to the 2t, I think, right? Yeah. So 4 is a 2t plus 4t e to the 2t. All right, not too bad. I think I need to do the cross product. All right, so what I'm gonna do, I line up. I don't need to write down another matrix. So this is I, J, K. I, J, K. All right, so the first one will be negative 2e to the negative 2t. Right. That's the I. Wow. J is the first column, last column, first column, last column, and put the J here. And K and K. Now I hope we are able to simplify it. Okay. I think the first term is not too bad. You know, if you do the calculation, do the 2t times e to the negative 2t is going to be, yeah, let's do some scratch. 4 plus 4t. And then I have to minus 1 plus 2t. Okay. Yeah. So I got I think it's going to be negative 12 minus 16 I. So the e is gone actually. Right? And then the next one you will get you have a e to the 2 here. So the next one will be, let me see, 4 8 plus 8t minus 4 minus 8t. Okay? Yeah, so it's going to be just 4 e to the 4t. Okay. Finally, I get 8 minus negative 8, so 16. So we get a cross product. Okay, so that's, and you can verify this is a perpendicular to, yeah, it's perpendicular to no, that was a computation mistakes here. The middle term, okay? I'm trying to look at the dot product was gamma. Oh, it was gamma prime t, yes. I think that's correct. It's gamma prime t. Yeah, I think so. Okay. So then you just normalize that, and you get 3. You can have a, yeah, you can have a, the formula as a general formula. The first one is this just the derivative. And the normalization, I think you can take a common factor out, no? And that will be 4e 4t minus 4e to the negative 4t and plus 1 plus 2t squared e to the 4t. So I started to simplify it further, but the cross product looks much simpler. If you want to use this notation, vector notation, and just, right? And then the normalization is negative 12 minus 16t squared plus negative 4 e to the 4t squared and plus 16 squared. Then if you're at some particular point, you can plug the number for t, then you get. But anyway, so for every curve, as long as the first derivative, second derivative, they're linear independent, you can get 2 special vector associated with that. Okay. Now I'm going to look at a special case. Okay. Assume that this is always equal to 1. Okay. So in that case, what we can get? Right. So that we call unit speed curve, right? So in this case, t is again just itself, right? No question, right? Because the denominator, you normalize the denominator is going to be the length is going to be 1. Okay. All right, so what is next? The gamma product is dot, right? So this is gonna be 1. So you differentiate both sides. If you differentiate both sides, then you derive some interesting formula. Now this is using the product rule. You get twice gamma prime t, gamma double prime t. This is the right hand side 0. So what does that tell you? This is a second derivative. So the second derivative actually is perpendicular to the first derivative. Okay. So you get a vector. You get a vector. The second derivative is perpendicular to the first derivative. All right, and imagine the length of this second derivative actually tells you how fast the curve bends into that direction. So in geometry, in this case, the length of the second derivative we call the curvature. That makes sense, yeah. All right. And you can, yeah, we're going to talk about this later, yeah. Then, so this is second derivative, right? The length of the second derivative and direction second derivative gives you some information about the curve, Right. If it's a strict line, no bending. Okay, it's a strict line. It's a gamma of t is going to be a linear function, right? Gamma of t. So the special cases, okay? If gamma of t equals at plus b, where a has a unit length, right? So in that case, as you can see that this just itself, okay? The second derivative is almost 0. It's always 0, 0. So that means the curve is not, it's not bending in any direction. It's flat, okay? It's a straight line. So the second derivative really should be considered as the length should be considered as curvature of the curve in some sense. Okay, that's the first example. Second example is going to be cosine r cosine t a plus r sine t b, where a b equals 1, a dot b dot is going to 0. Okay, so that means in the space we have a 2 perpendicular vector. And this is a t, so we're talking about the circle in the plane spanned by A and B. So what is my second derivative, right? Its curve is going that direction. Right. So gamma prime t, I'm sorry, I have to divide by this, I have to add divide by r here. Yeah, otherwise I'm not going to get a unit tangent vector, okay? Prime t, I get negative sine t of r, that's A, plus cosine t of r, that's B. All right, so this is a tangent vector. Let's calculate the length. The dot product with itself is going to be the length square of the length. All right, this is going to be when you do the cross product, right? It's going to be negative sine t of r square. It's a dot with itself, and the minus twice of sine t of r cosine T of R A dot B and plus cosine square T of R. But the one in the middle is going to be 0. So this is going to be 1, this is going to be 1. So it's negative sine T of R square plus cosine T of R square. That's going to be 1. So it's indeed a unit tangent vector. Okay. So what is our second derivative? Second derivative, you can continue to differentiate. It's going to be negative, so it's negative R 1 over cosine, right? And then negative 1 over sine T of R. I think this is second derivative. All right, so the second derivative is not a unit. And the length is going to be 1 over R, actually. Right? And the uniform, it's always a constant. So if you look at the picture, okay, this A, this is B. So this is a rotation circle. So this is a tangent vector. And the second derivative actually is pointing in that direction. Okay, and the length of this depends on how far away of the curve from the center. Okay, if the radius is increased, then the length is getting shorter. Okay, so the circle is more flat. So that gives me some idea how to introduce the curvature of the curve, because at least those two examples tells me this probably is the right notion. The length of the second derivative should be viewed as curvature. Okay, because now the circle is evenly curved. Yes, now the curvature is constant when not R. Right? How does a mathematician do it? So early days, you learn the calculus, you are finding derivative. So now you're going to use the calculus to study the nature, right? The geometry. And you needed to describe something using a number. Describe we call it curvature of a curve using a number. You cannot say, oh, this is more curvy than that. Yeah, obviously more curvy than the other one. But you have to use a number to how to do it, right? Just like 5,000 years ago, humans were trying to coming back to collect some apples, then you cannot. You have to know how to do counting, right? That's not easy. Monkey cannot do that. I got 5 apples, the other guy got 3 apples. Another one got 22 apples, and how to record it. You cannot say many apples. Okay? So they have to find the recipe. Because we have 10 fingers, so that's why it's easy to introduce a qualification numbering system. Okay, so more advanced geometry, this is what happened 200 years ago. Some people start to think about this problem, right? And you want to use a number to describe how the curve. All right. So we probably come back about the curvature. Okay. So you have to begin with special. You have to begin with a special parameter, right? Make sure that the unit speed. And if it's not unit speed, this
a little bit more complicated. All right, I'm going to look at the help. Helix R cosine R cosine T sine T, and this is let's use let's use the A and the B and B. Okay, that's more general. All right, so R power T equals negative A sine T and A cosine T and the B. This is the length. First thing I want to see, the length is going to be negative A sine square and A cosine T square plus B square. It is going to be constant. Constant is good, it's easy, we can normalize. So this can be A square plus B square. Okay. It's not going to be what in general. What am I going to do? In order to get unit, so the unit tangent vector will be here, it's going to be gamma plus T normalized. Right? So that is going to be A square plus B square, negative A sine T, A cosine T, and the B. Okay. Because it's a unit, if we do not reparameterize this parameter, this is not going to be unit, right? You do get a unit tangent by dividing the mix, but I cannot use that to get the second thing. It's still called color, right? So this is that, but we have to assume that unit unit must be unit, right? So it's not unit. It has constant. Okay, so at least you get unit tangent, and where is its point? Right, where is its point? So this is going this way, right? So at the point, this is down, and this is going to change. So it's point upward, right? Point upward. But this curve, it sounds like this curve is curved evenly. Okay. So I guess if it has curvature, then the curvature should be constant. Okay. But this is not a curve in the plane. It's not plane. All right. So if we want to find the second derivative, and we will get negative A cosine T, negative A sine T, and 0. So the second derivative is a horizontal. So this gamma property and this gamma property. Yeah, this is the gamma property. Okay. All right. Now, now there's so this it's clearly okay. It's perpendicular to each other, and we can prove that as long as the tangent vector is constant length, the second derivative must be perpendicular. Okay, perpendicular to the first derivative. Okay, but then the length. Okay, the length is also has constant. Okay, it has a constant. Okay, it has a constant. That's going to be A. So you can normalize. Yeah. Now I'm going to for the same term, there are many ways to describe. So since the tangent vector is not a unit vector, so I cannot view the second derivative as a curve. Okay, I needed to reparameterize it. Okay, so I'm going to start gamma. I use a gamma theta, or I can use a new parameter. Okay, this can be A cosine and square B sine S square S square and the B square S square. Now, if you use this, you get the same object in a space, but the derivative, this is going to be negative A square and sine, right? And get the B, it differentiates cosine S, and then, all right, so it looks more complicated. However, the length is going to be only one, okay? So the length is just one. Why? Because it's a square, right? Let's look at square. Then the square base component. Sine and it has B square cosine term, the theta, and the C, and square. So the first part is the sine square plus cosine square is always one. So you get A square and here B. Okay, square. Finally, that's the one. You see, that's the reason I have to divide the parameter by a square ratio. Yeah, this is called the midterm isolation. In other words, there's a moving object in space. Originally, it's fast or maybe slow, but that's constant speed. So you put another moving object there along the same orbit, but at the unit speed is the given speed, which is one mile per hour. So now you have a two moving object, but only the one with the speed, not only just curve speed, just speed equal to one. I can use that to measure the curvature of this orbit. Okay. The second derivative, if I was to find the second derivative, then what I got. I think make it fine because I want to do A. And I think it's square and become cosine. Okay. And this is A. And the third term is 0. Okay. And then this tells you when you spread, it's just equal to, I think it's A squared plus B squared plus color. This is still A. Okay. Oh yeah, I just saw it. Nothing. There's only one step. Okay. I'm still up to squared just this. Okay. Yeah, this is let me go back. I think I made a mistake here. This is the origin. Yeah, this is the A here. That is A here. Okay. Yeah, then it's correct. Right, so this is it's a constant. This is should be viewed as so much. Okay. So now we are going to let's consider gamma t, y, t, and z, t. We find the derivative. You know, when the derivative is going to be the new vector each component, right? You have to differentiate component. But you can also look at the integral. Integral is also a vector, but you just evaluate integral for each component. Okay, that's our definition. So if you specialize from A to B, then to be A to B, A to B, okay. And so you just need to evaluate, each component, right? So if I use the IJK, then I integrate, integrate each component. Okay, so let's take a look at example. So if gamma t equals 2 cosine I plus sine j plus 2tk, I can use IJK. I can just use the standard notation for the vector. Okay, let's find out. Find the integral from 0 to pi. Okay. But that's going to be integral of 2 sine cosine t dt from 0 to 2 pi I, and integral from 0 to 2 pi sine dt and j, integral from 0 to 2 pi 2t dt and k. Well, the integral of a cosine t, integral of sine t over the whole period from 0 to 2 pi is going to be 0. So it's 0 I, 0 j, and the 2t is a t squared from 0 to 2 pi. The antiderivative t is t squared. So that is going to be 2 pi squared of squared, right? Right. So we also have a similar formula for any. If you integrate the tan inverse, right? This will be, it's still same as, the integral of, right, x prime t dt, integral y prime t dt, and integral of t prime t dt. Okay, so according to the formula in calculus, let's just x v minus x a, y v minus y a, v b minus v a. Okay, and you can separate again. So you get xb, yb, and vb. Yes, xa, ya, va. So we use a formula for one for, for function of the vector function, right? So we get this. This is gamma b. So we have a similar identities. Okay. In particular, if it's closed curve, okay. So in particular, if it's if the starting point equals any point, right? Right. In this case, so if gamma b equals gamma a, what does that mean? That means coming back to this point, right? Then the integral of the tan vectors can be 0. Okay. All right. Uh, so I want to go back to the reparametrization problem. Okay, so you have a curve, right? You have a curve. Maybe originally the curve is not, it doesn't have unit speed. Right. So you have a, what do you have? You have a curve T, and maybe this another vector, second derivative, but this angle is not necessarily the right angle. Okay, in general, T is not, yeah, in general, it is not the particular to gamma plus, unless it has a constant speed, right? But if gamma probability has constant length, and then gamma probability to gamma in this case. Okay. Okay. So we try to let me prove this fact again. Proof. Right. It's the same idea. Proof is constant length. So this will be constant, right? So you differentiate both sides. The left-hand side is going to be apply the product, right? Differentiate both sides. This the right-hand side 0. The derivative constant 0, so that implies the two vectors are perpendicular. Right? When you differentiate the left-hand side, product of two vectors, and we have a similar product rule for the product, so that's why I get twice, you know. And also commutative. So A times A dot B is going to be dot A. Okay. So that's the end of the proof. Very well, right? But in general, it's not true, right? Even in this case, I cannot use a second derivative curvature. I'm going to reparameterize it. Yeah, reparameterize is a little bit difficult concept. For the same point, I described I left S to be S of T. It depends on T, such that gamma 2 dot S is going to be always equal to gamma T. All right, so that means S of T gamma. Okay, so that's the relationship. So that gamma and the gamma 2 dot they have the same orbit. Just one goes speed faster than the other. Okay. Okay. So gamma and gamma 2 dot have the same orbit, okay, in the space. Just one is, look at the example I laid it, right? Okay. They have the same orbit, just one is faster and one is slow. So that's it. Okay. And these two parameters are related, okay, such that this is the first one. Second one, I want to make sure this new one is always constant. Okay. Can we do that? Yes, the answer is yes. We can always find such parameterization. Okay, how do you do that? Well, you differentiate both sides with respect to S. Right? Then, since this is a unit, okay, so this is a unit here. So it's going to be, so you can find the parameterization using pattern. Okay. Okay, so this is an important formula. You can determine it. Okay. How do you determine S? You integrate both sides, right? You got S minus S, the integral frees up, right? So that's why how do you find the new parameter? It's not easy to integrate, okay? All right, so we got this. Then yeah, let me go back to this. This is my formula, right? Just simply, remember S is a function of T, right? All right, so I'm going to differentiate with and dSdt, that's the relationship, then I differentiate twice. But then I have product rule. All right. I'm going to do cross product. So gamma prime times gamma prime. Okay, so this is going to be this plus that, and then DSP and Q. And this plus that is going to be zero. So that's what you have to decide. All right, so the cross product does not change the proportion to each other. Okay. So what I got here is an interesting thing. I got this is a gamma power S, gamma dollar power S, the gamma power T plus gamma dollar power T, and the DSD T and Q, right? So we derive some formula here. So DSD T Q is gamma power T, right? And then all right, so that's great. We know that this gamma, this is going to be what? We also know that this is going to be equal, right? That's the part. And then we know that the second derivative, the length of the second derivative is kind of like, it should be viewed as curvature, right? Okay. So yeah, curvature, what is that, right? I put the curvature here, okay? All right, so this is identity. Interesting. Since it's a perpendicular, if you take the norm, what do you get? Okay, so you will get okay. So then this is since first with length and actually this is gamma. All right, so that's it. So this is a formula. The length of the second derivative for the new parameter is going to be fixed. So this we derive this formula, and T is an arbitrary parameter. Okay, T is arbitrary parameter. Okay, if you look at the picture, here, this is gamma parameter, and this must be perpendicular, but it's maybe short. But the plane spanned by that is the same as the plane spanned by gamma. Okay. So this is a plane spanned by this. It's also spanned by, yeah, it's also perpendicular by gamma. So we will go back to the topic later. Okay. All right. Let's stop here.